Today I'm going to talk about moment-generating function. So yes, let me write down the name and also just to relate some material that we did from last time. Yeah, so in last lecture, we talked about the moments. A question? Maybe I'll try write in a bigger size. Okay, yeah. Yeah, so yeah, in last lecture, we talk about random variables, and we specifically calculate the E of x and the expectation of x and the expectation of x squared. And then we call them the first moment and the second moment. And we also mentioned a little bit about the kth moment, which is just x raised to the power of k. And for this kind of random variables, and also for the moments, there's also a function that is called the moment-generating function, and then it means that the function can help you to generate the moments. Yeah, and the moment-generating function is also very helpful on recognizing the distribution of random variables. So intuitively is that if you know the moments or all the moments for particular random variables, then you essentially know how to describe a random variable, and that gives you information about what this distribution that this variable follows. So that is the idea to calculating the moments. Yeah, and also I think this is also related to someone asked about this last lecture. Yeah. Okay, so today we're just going to focusing on the moment-generating function for different random variables. Okay, so let's start from the definition of a moment-generating function. So usually we write as a capital M. Is this size okay for you, for the people in the back? Okay, good. So we write a capital M as the name of the function, and then we usually put a subscript just to referring what kind of variables that we're talking about. And this is referring to the random variable x. And also, this is a function of a parameter t. So yeah, so this will be our notation for the moment-generating function. Yes, and then for the definition, and also it will be depends on whether this is a discrete random variable or a continuous random variable. So yeah, so maybe let me first write down the general formulation for the moment-generating function, which is the expectation of a function. And this function is defined as the exponential of t multiplied by x. So again, so moment-generating function is a function with respect to t. And this, the x here is referring to which variables that we are talking about. So later on, we will talk about a joint moment-generating function. So we will have multiple random variables. And then you will see like x1, x2, or x or y, that kind of differences there. Okay, so moment-generating function can be expressed as expectation, and then we can reuse our definition for the expectation from last lecture to further elaborate this moment-generating function. So again, for the discrete case, using the definition for the expectation is that you need to sum over all possible x in the support, and then this is the function e raised to the power of tx, and then multiply by the probability mass function. So this is for discrete case. And what we are doing here is just using our formula for the expectation that we introduced last lecture. Okay. And then also for the continuous case, I'm not sure if I can erase. Maybe I should sit down. Okay. Yeah, so we are just applying the definition of expectation with respect to a function. So you can consider E of tx as the function. Maybe we can just bring up this part. So if you want to calculate expectation of a function, you essentially just have the summation of that function multiplied by the probability mass function, or the integral of that function multiplied by the probability density function when you evaluate the integral. So here, for the moment-generating function, the g of x is referring to e raised to the power of tx. So you can just replace the gx to e to the power of tx. Give me 1 second. Okay. That's that. Let me also just complete e raised to the power of tx, and then f of x for the probability density function, dx, and this is for the continuous case. Okay. So this is more of a, just like a definition. Okay. So next we are going to elaborate, or just to give you an idea why this function or this particular function can help you to generate moment, as the name indicates, moment generating function. So the idea again is also revisiting the expression for e raised to the power of x. So last time we rewrite, or we express this e raised to the power of x as an infinite sum. So let me write it again. So let's use index n here, starting from 0 to infinity. And then we have this particular fraction, n factorial. So this is also the expression that we use to solve some of the expectation from last lecture. And again, we are going to use this to illustrate why this function is helpful in generating moments. Okay, so maybe let's first write down a few terms for the first few terms in this sum here. So when you bring in 0 equal to n equal to 0, the first term is equal to 1. And when you plug in n equal to 1, you will have x raised to the power of 1 over 1 factorial, which is 1. And then for the second term, when n equal to 2, you will have x raised to the power of 2 and then over 2 factorial, which is 2 multiplied by 1. And then for n equal to 3, you will have x raised to the power of 3 and then 3 factorial, which is 6. So maybe I keep the factorial here. Yeah. And then this is an infinite sum. But for the moment generating function, what we have here is e raised to the power of tx. So what you can do here is that you consider the x as tx here. And then you replace all the x with tx in this infinite sum. And then you will result in this particular expression. So again, for the first term, when you bring in 0, the first term is equal to 1. And when you bring in n equal to 1, you will have tx raised to the power of 1 and then 1 factorial. And then for the second term, you have tx raised to the power of 2 and then 2 factorial plus tx raised to the power of 3 and then 3 factorial, and then infinite sum. So now we are going to plug in or replace this term into our formulation or our definition for the moment generating function. Okay, so now let's start from the moment generating function, and we are going to use the discrete case for this illustration. So again, the definition is you need to sum over all possible x, e raised to the power of tx, and then multiply by the probability mass function here. And what we are going to do is that we're going to replace this e raised to the power of tx with the infinite sum that we define here. So again, we have the summation here, and let me use a square bracket to cover this infinite sum here. So you will have 1 plus tx raised to the power of 1, 1 factorial, and then tx raised to the power of 2, and then 2 factorial, plus tx raised to the power of 3, and then 3 factorial, and then dot, dot, dot for this infinite sum. And then don't forget to multiply your probability mass function, the p of x. Next, we are going to distribute the p of x, or the probability mass function, to each of the term in this infinite sum. So we have a summation for all possible x, and let's see if I want to keep the okay, so maybe I will also not only distribute the p of x to each of the terms in this infinite sum, and I'm also going to distribute this summation notation. So we have summation of 1 multiplied by px. So the first summation multiplied by 1 and the px. And then for the second term, you will have, again, the summation, and then t of x raised to the power of 1 factorial multiplied by px. And then again, summation for all possible x, and then tx raised to the power of 2 factorial multiplied by px. And then let me just use okay, sure. Okay, so what we did here is just replace the e of x with the infinite sum, and then we end up with this expression. So now I'm going to make, is there a question? Scroll up. Here. Oh, I'm going to post all the materials. Yeah, so let me just summarize. So here I just give a definition for the moment function, and this definition can be expressed in terms of expected value here. And this expected value is interested in a particular, is circled around a particular function, and this function is called e raised to the power of tx. And to further analyze this particular function, we're going to use this infinite sum to rewrite this e of raised to the power of tx. And then we plug in here in the square bracket, and then we end up with this notation. And next, we are going to further analyze this expression and see how it can help you to generate the moments. So that's what we did so far. Okay, so let me first make comments or mention a result here. Is that if you want to find a particular moment, let's say the kth moments for a function, all you need to do is just take the derivative of this momentary function. So here I use a parenthesis for the superscript for k here to refer that you need to take the kth order derivative for this function. And again, this function is a function of t. So when you take the derivative, you always take derivative with respect to t for this function. So you can see that in this expression, it's a function of t. So when you take the kth order derivative, you always take the derivative with respect to t. So yeah, I think that's the, when I first learned it, I always forget when taking derivative what to work on. So I always like to emphasize that it's a function of t. So you take the derivative with respect to t. Okay. So that is our result here. And next, I'm going to show you why taking the kth order derivative for this expression will end up with the kth order moments, or the kth moment here. So yeah, so last time we used the definition of expectation to calculate the first moment and second moment. So here I'm introducing another way to use the momentary function, and then you can take the first order derivative, and then you will receive the first moment. And if you take the second derivative of this function, you will end up with the second moment. And if you want to take the kth derivative, you will end up with the kth moment for this random variable. So this is just another way that you can calculate your expected value or the second moment and then calculate the variance. Yeah. Any question up to this point? So yeah, here I'm just introducing the idea of momentary function. So now we are going to look or to take a look on why taking derivatives can help you to generate those moments. Okay. Oh, another thing is that you need to set the t equal to 0 after you're taking the derivative. Yeah. So don't forget, there are two procedures. First is that you take the derivative at the corresponding moments. If you want the first moment, take the first order derivative. If you want the second moment, take another derivative. After you have the derivative and then set t equal to 0, you will end up with the moments that you want. Okay. So maybe let me put the result 1 here. Okay, so next we are going to see why this is the case. Okay, so now maybe I can put it as an example. So here, suppose we want to find the first moment. So we have expectation for x raised to the power of 1. And then like what we said, we are going to take the first order derivative. So I'm just going to use a m prime referring to the first order derivative. And then set t equal to 0. Okay, so now we are just going to take derivative for this expression, set t equal to 0, and then see if it's going to give us the moment or not. So let's verify about that. Okay. So here, this summation here is the first term. So when you take the derivative, again, with respect to t, what do you get for the first term here? So let me circle the first term. When you take derivative with respect to t for these terms, what do you get? You should get 0, right? Because it does not involving t. Yeah, okay. Then what about the second term? Let me circle this. When you take derivative with respect to t, what do you get here? Okay, and don't forget the summation there. Yeah. So you have x times px. So what does this expression reminds you of for a discrete case? This is essentially the expected value, right? By definition. Okay, but let's circle back afterward. Okay. Then for this term here, when you take the derivative with respect to t, what do you get? So you can remove anything not involving t outside. So you essentially have t squared. So when you take the derivative, you end up with that multiplied by px. And don't forget the summation here. And let's see if we can further simplify this. So 2 factorial is 2, cancel out with that. So you will have x squared multiplied by t multiplied by px. Is that correct? Okay, so maybe let's do one more term here. So let me also include the fourth term, which is for tx raised to the power of 3 and then 3 factorial px. Okay, and then plus dot dot dot. So for this term here, when you take the derivative with respect to t, what do you get? So again, you can remove everything not involving the t as a coefficient, 3 factorial, and then the only thing is t raised to the power of 3. So you will have 3t raised to the power of 2 multiplied by px. Okay, so, and then also don't forget there are infinite terms here, so you need to plus dot dot dot. But the things is that here, I'm making the claim that when you set t equal to 0, this should give you the first moment. So let's see, when we plug in t equal to 0, do we get expected value of t for x or not? Okay. So we have a 0, and then as we mentioned earlier, this term will reduce to the expected value for x, right, by definition. And this term here, you can see that it's involving a t, but now we're going to set t equal to 0. So what does this term will result in? Just 0, right? And what about the next term here? 0. Okay. And then you have lots of 0, and then you will end up with the first moment here. Okay, so that is the intuition, or more of a demonstration on why this function, and then by taking two procedures. One is taking the kth order derivative, and the second step is to set t equals 0. You will end up with the corresponding moments that you want. Okay, any question up to this point? Okay, so next, let's also try the second moment. So by our result, we should only need to take another derivative from here, set t equal to 0, and let's see if that will give you the second moment or not. So here, let me use double prime to referring to the second order derivative. Also, let me know if any notation is unclear. I'm always worried about my handwriting is terrible. Okay. So what we want to do is we want to check whether the left-hand side equal to the right-hand side. Okay. Okay, so now let's take, so here, this is already the expression after you're taking the first order derivative. So all we need to do is just take another derivative for this expression with respect to what here? What should we take? Which variable should we take with respect to t, right? Okay. So for the first term, which is a 0, it does not involving t, it will give you a 0. Now for the second term, when you take another derivative, what does this term end up? There's no t here, right? So you take a derivative with respect to t, it will give you another 0. So starting the third terms, it started to involving t. So now when you take the derivative with respect to t, what does this returns? Summation of x, yes, times 2 px. Okay, yes. So that is the third term when you take derivative with respect to t. What about the fourth term here? So these can be considered as the constant. And you also have a 3 here. The 3 is coming from your first order derivative. So now you want to take another derivative. So what does t squared? What is the derivative of t squared here? Times 2 times t. And then px, right? Okay. And then don't forget this is an infinite sum. Okay. But the remaining term, they all should involving a t from after the fourth term. Does that make sense? So I'm just not going to write it right down. If you want, you can also try to write down the fourth term from your homogeneous function here, take a first order derivative, and then take another derivative just to verify if you want. Yeah, but but all the remaining term was again involving t. So when we set t equal to 0, all those terms involving t will be disappear. Okay, so now let's further analyze the second order derivative for this function. So you have a 0 plus a 0, and then starting the third terms, you will starting to have something non-zero. And what does this returns here when you cancel out all the coefficients or all the constants? So the third term here, what does this give you? X squared multiplied by px. And what does this remind you of? By definition, just the second moment, right? And then for the rest of the terms, they all involving a t. And when we set t equal to 0, they are all just 0. So this also checks out our result when you take the second order derivative you will end up with a second moment after you set t equal to 0. Okay. And if you want, you can also keep taking derivatives, and then you will see that this result here. If you want the kth moment, you just take the kth order derivative for this function, set t equal to 0, and then you will get the kth moment. Yeah. So, yeah. Any question or comments? Okay. So, yeah. So literally, moment-generating function is just used to generating moments. Okay. So next, we are going to revisit the examples that we did from the first lecture, and then using moment-generating function to calculate the first moment and the second moment, and then calculate the variance, and see if we get the same thing from last lecture. Yeah. So any question or comments before we proceed? Okay, so I think for now, maybe I can use the second example from last lecture. So in last lecture, we used Poisson distribution for the discrete case and the exponential distribution for the continuous case. So since I introduced the moment function using the discrete random variables, so here I'm just going to use a continuous distribution for our example here. So again, for exponential distribution, what is the support for x here? Also from last lecture. What is the support for x? Sorry? Sorry? Oh, what is the support for x, for the x follow exponential distribution? Yeah. Any constraint on the parameter lambda? Yeah. So all these things, maybe it looks trivial for now, but if you want to proceed to graduate school, and then if you're working on these distributions, properly defining these things will play a very important role in your research. So yeah, so maybe you might think I'm asking very a silly question, but I just want to like provide you the habits of always pay attention to all these details, as they might be useful in the future for you. Yeah. Okay, so last time, let me just put down the result from last time. I think we have, we show that this is equal to 1 over lambda. And then for the second moment, let me double check. What do we have from last time? Second moment is 2 over lambda squared. So what we did is that we're using a definition for the expectation to calculate these two quantities. And what we're going to do now is that we're going to use the moment-generating function to calculate these two quantities again. And let's verify whether it's equal to 1 over lambda and 2 over lambda squared or not. So that is our goal here. But first of all, we need to define or calculate what is the moment-generating function for an exponential distribution. So what we did here is referring to any arbitrary probability distribution. So here we did not particularly specify what this p of x, the closed form solution, or the closed form expression for this px. So next, when we are talking about any particular probability distribution, we need to consider the form for this px, and then we need to plug in the formulation for this distribution to replace all the px here. So that is another thing we need to do here. Okay. So anyone still remember what is the probability density function for a exponential distribution? It's also from your last lecture, which is this one. that we work with. So the lambda is the parameter, and exponential raised to the power of negative lambda multiplied by x. And also, if you want, or sometimes when in your programming language, you probably will want to write something like that. Yeah. So I'm going to use these two notation interchangeably based on whether the if I want to emphasize the power or to emphasize the this is an exponential thing. Yeah. But these two are the same. Okay. So now, or for our first step, if we want to use the moment function to evaluate the first moment and the second moment, we first need to calculate the moment function for a random variable that follow an exponential distribution. So to construct or to specify the moment function, here we can again use the definition for the expectation. So what we have is this function gx multiplied by f of x, and in our case this gx here is e raised to the power of tx, like we mentioned earlier. So that's that, and then we need to multiply by f of x for this probability density function. Okay, so we need to plug in lambda e raised to the power of negative lambda multiplied by x and then dx. And then we need to evaluate this integral and then ends up with a formulation. And then this expression will serve as our moment function. And then we're going to take derivative for this expression to calculate these two quantities here. Okay. So that is what we're going to do next. Any question or comments up to this point? Okay. So let's see. Maybe we can first group the two exponential terms together and then resulting in lambda e exponential of, so again, e raised to the power of a multiplied by e raised to the power of b, this is equal to e raised to the power of a plus b. So here in the exponential, in the exponent, we have, let me write it in this way. So lambda minus a t, and then closing that, and then the, am I missing an x? Yes. Yeah. Lambda minus t multiplied by x, and then maybe I can use a square bracket just to distinguish between these two, dx. Okay, so yeah, one thing to comment here is that when you work on moment function, you always taking the derivative or talk about the parameter t here. And then when you talking about the expected value, which is this e here, you're always talking about random variable x. So just to make sure that when you work on the expected value or moment function, make sure that you know what are the terms that you are working on right now. Otherwise, if you mix the terms that you take derivative or taking the integral with respect to, then it is very likely to make some error over there. Yeah. So when we talking about the expected value, we are taking the integral with respect to x here. Okay, so we end up with something like this. And then any thoughts on how to evaluate this expression here? Last time when we introduced the first moment and the second moment, we used something like integration by parts to evaluate that. So yeah, So any thoughts on any techniques on how we can evaluate this particular integral here? Yes, yeah, we can do something like that. So yes, thank you. Yep. So yeah, there are different ways that you can evaluate the integral, and we are going to use that. I think, is there a name for that? Like change of variables, or maybe I would just call it change of variables. Okay, yeah. So yeah, what we can do, or one way that we can do, is that we introduce another random variable called, or not random variable, but variables in a mathematical sense. We set u equal to the things in the exponent here. So I'm going to set u equal to lambda minus t multiplied by x. Okay. Then we can rewrite x as, let's see, 1 over lambda minus t multiplied by u, so that dx is equal to 1 over lambda minus t multiplied by du. Okay, so now we have all the necessary components. We're going to change this as u, and then this dx with this term involving the du. Okay, so now let's plug in the corresponding terms here. And also this lambda here is not related to this random variable x, so we can consider this as a constant, move it outside the integral. So from 0 to infinity. And what we left inside the integral is the exponential of negative u, and then another coefficient 1 over lambda minus t, and then du. Okay, so we can further bring this coefficient outside, as it does not involving any random variable x here. So or u here in our case. So yeah, so again, always pay attention to what operation you are doing right now, and then what is not random or what is constant, so that you can move it outside. So in our case, the things involving the t can move, is regarding as a constant, you can move it outside. So you have the first lambda here divided by lambda minus t, and then integral from exponential of negative u du. And what is the upper bound and lower bound here? After we change from x to u, what is the upper bound and lower bound here? 0 to what? Why is that? So you're saying the bound should be evaluated from 0 to u? So one way we can think about this, or to identify what are the bounds, is that we can revisit our original function. So this is for x equal to 0 and x equal to infinity. So we still want to evaluate this integral for x between these upper bound and lower bound. But what we did is that we make this change to write it as u. So one way you can do is that to plug in the lower bound, set x equal to 0 into here, and let's see what do you get for u. So if we plug in x equal to 0 in here, what do you get for u? 0, right? And now for the upper bound, when you plug in infinity for x here, what do you get for u instead? Yeah, but it's infinity, right? So after you change the variable from x to u by using this kind of like a change of variables techniques, then to evaluate or to identify your upper bound or lower bound, one way you can do is just plug in the bound for your original random variables, and then plug into this the things that you change, and then see what will be the new upper bound or lower bound. So in our case, it's from 0 to infinity. But this is with respect to u here, because this integral is with respect to u. Okay, then any thoughts on how to evaluate the integral here? Okay. So I think after we make the change, this would be easier to evaluate integral. So any thoughts, or what would be the result for that integral? So what is the integral for exponential negative u? Or what, when you take the derivative with respect to u, will ends up with exponential negative u? That's another way to look into this integral. Sorry? Negative exponential exponential of, okay, yeah, thanks. Yeah. So you can always verify that if you take derivative here with respect to u, so you will have a negative sign cancel out with that, and then that will be that, yeah. So maybe let me use a square bracket to cover this. So this, inside the square bracket is the result from your integral. And we want to evaluate, again, u from 0 to infinity. So what does this give you? So maybe let me put -1 for now, and then e raised to the power of u, and then 1 over that. So maybe this will give you a better idea when you evaluate from 0 to infinity. So any thoughts? So when you plug in infinity, what does that give you? Inside the square bracket, when you plug in infinity. So basically you have a very large number in the denominator. So that should give you a 0, right? Yes, 0 minus 1. Yes, perfect. Thanks. I was thinking about that. So it should be 0. Okay, so maybe just be, yes, minus a -1. Is that correct? Yeah. So you will end up with lambda over lambda minus t. So this is the moment generating function for a random variable x that follow an exponential distribution. So as you can see, this is a function that involving t and also the parameter. So this particular expression is the moment generating function for a random variable that follow exponential distribution. Another thing that we also mentioned a little bit is that moment generating function is used to, or can be used to identify a distribution. So whenever you work with another new random variables, and if you calculate the moment generating function, and then you end up with this particular expression, then you can immediately identify that the new random variable that you're currently working with also follow an exponential distribution. So that's another theorems. I think people usually call that the uniqueness theorems. So all the distribution will have their own unique moment generating function. So let me just say that again. So if you're working with some other random variables, and then when you evaluate the moment generating function, and then you find out that, let's say, it ends up with this particular expression, then you immediately know that the new random variable that you're working with already follow a exponential distribution here. And later we will calculate the moment generating function for different distribution, and then you will see that they all look in different ways. But if you find a moment generating function that you look familiar, then you already know that what is the distribution that random variable follows. Yeah, so that would be the idea. Okay, so any question up to this point? So we are not done yet. We just calculate the moment generating function. But our goal is that we want to take the derivative and the second order derivative and see whether we can result into these two terms particularly. So that is our goal here. So our first step only is to calculate the moment generating function, and then we already have it. Any question or comments here? Okay, so let me also change a little bit on the expression for this one. So so one way you can change this fraction is that you can also write it as lambda multiplied by lambda minus t raised to the power of -1. So so maybe this expression can help you to, when you take derivative with respect to t, maybe this expression will be a little bit helpful to ease your notational, in a notational wise. Yeah. And sometimes you will also see people writing the moment generating function in this formulation. So t over lambda raised to the power of -1. But they are all the same. It's just using different way to express the same formulation. Yeah. Okay, so next, let's find the expected value. And our goal is that we want to verify whether it is equal to this or not. And what we are going to do is to take the first order derivative, set t equal to 0, and we want to check whether equal to that. Okay, so now we're going to take the derivative. So what variables should we take derivative with respect to here? T. Okay, so maybe we use this expression. So when we take derivative for this expression with respect to t, what do we get here? Yeah, maybe we can work on the terms one by one. So here, when we take derivative with respect to t, the lambda is just a coefficient. So we have a lambda immediately. And then here we have a exponent, or with a power of -1. So we can bring it a -1, maybe use a parenthesis to represent a negative sign. And then we have this one. You can consider it as a chain rule. So is it called chain rule or product rule, or sorry, okay, yeah, chain rule, okay, yeah, and then minus a t, but here you need to raise to the power of -2, and then again using the chain rule, you need to take derivative with respect to the terms inside the parenthesis, and this will give you another -1, right? And this will end up with let's see which way is easier. So maybe let's write it. Okay, so maybe this, maybe write it as a fraction again will be easier for evaluation. So yeah, so which notation or which expression you want to use is really based on your need here. So maybe I'm going to use fraction again. So maybe this expression can be helpful when you take derivative, but maybe when using fraction, will be easier when you're evaluating the, yeah. So what we're going to do here, after we're taking derivative, what is the second step in evaluating the moments? Oh, yes, yeah, thank you. Yeah, yeah. So Yes, yeah. What are the second step we need to do here? So the first step is derivative, first order derivative, and the second step is, yes, at t equal to 0. So what does this term will gives you? Okay, so what we did here is that we use homogeneous function, taking the first order derivative, set t equal to 0, we end up with 1 over lambda, and this will also returns the first moment that you derive by directly using the definition of expectation. Yeah. So now we also verify that with a specific distribution, it also return the intended moment here. Yeah. Any question or comments here? Okay. So next, okay, I think here we are going to find the second moment using homogeneous function. So we are going to take another derivative. Let me use double prime here, set t equal to 0. So we already have an expression here for the first order derivative. So all we need to do is just take another derivative for this expression with respect to t, and then set t equal to 0, and let's double check, or let's verify what that expression will give you. Okay. So now maybe let me use the the products again. So minus a t raised to the power of 2, negative 2, and then dt, right? We are working with homogeneous function, so we want to take derivative with respect to t here. So this thing here is the first order derivative, and here we're just taking a second order derivative, or just another derivative here. So what does this expression give you? So maybe we can work on the terms one by one. So lambda here is a constant, or just a coefficient. And then you have a negative 2 in the front. Let me see. Yes. Okay. And then for the chain rule, you will have lambda minus t raised to the power of negative 3. And then you also need to apply the chain rule again for the terms inside the parenthesis. And then you have an additional negative 1 here. And let's simplify here. We should have, so the negative sign cancel out. We will have, so now let me use the fraction form again. We will have lambda minus t. So essentially 2 multiplied by lambda over lambda minus t raised to the power of 3, right? Yes. Well, what else we should do here? Set t equal to 0, right? And what does this give you when you evaluate t equal to 0? So 2 lambda over lambda raised to the power of 3, and then you will have 2 over lambda raised to the power of 2. I think this is also the solution what we have here. So both of them checks out. So when you use the homogeneous function and then taking derivatives at t equal to 0, you will also get the moments. Any question or comments? Yeah. So from now on, if the homework question or an exam was asking you calculate the moments or calculating the variance, you can use either way to do that, and then whichever you find is easier. Because as you see that in the last lecture, some of them can use like integration by parts, and then you need to evaluate the limits, and then you need to use the L'Hopital rules. Those can be very complicated. But once you know that the homogeneity function, all you need to do is just take a derivative set equal to 0, and then, for example, like in one line, you directly get your answer. From the last lecture, you probably need to evaluate the integral again and again, and then you calculating the limits again and again to get this 2 over lambda square. But here, actually, you just use one line, and then you can get the second moment. Yeah. So from now on, whenever the question or the homework was asking you to calculate those, you can just choose whichever is easier for you, and then start the problem from there. Yeah. Just to complete this example, let's also calculate the variance. So again, e of x squared minus e of x raised to the power of 2, you will have 2 over lambda squared minus 1 over lambda squared. And then this will give you 1 copy of lambda squared. And this is the variance for an exponential distribution. So yeah, just to distinguish that, when you take the derivative, you get what you call the second moment. But for the variance, is that the second moment minus the square of the first moment. Yeah. So yeah, I think this should conclude this example here. Any question or comments? Just wondering, do you guys need a break, or do you guys want to continue with some other examples? Oh yeah, by the way, I'm just wondering if this is too tedious for you guys, or if it is, or I mean, if this is new to you guys, or okay, good, yeah. As long as something new, then I can demonstrate something new, then that's good. I just don't want to demonstrate if you find this too tedious. Okay, can someone remind me when does this class ends again? What, sorry? 55? Okay, good. Then we have 30 minutes to go over some other examples. Okay, so we introduced the homogeneity function. We provide an intuition on why it can help you to calculate the moments. And then we also show that when you take the kth order derivative, it will give you the kth moments. And we provide one example for the exponential. And maybe let's work on a discrete case as another example. And also in this one, I'm going to using another distribution called binomial. And the parameter is n and the p. Okay, so any constraint on the n here? First of all, it has to be an integer, and then it has to be greater than 0. So that's that. Any constraint on p, which is the probability, let's say, in the context of coin tosses. So like you either, okay, so maybe let me take one step back. What is the support for x here for a binomial distribution? Oh, just the value that x can take. That's the meaning of support. Like, for example, when you evaluate the integral expectation for discrete case, so here is that x can take like from 0 to n. So here, this 0 and this n, or 0, 1, all the way to n, this thing here is called the support of x for binomial distribution. So whenever people was asking for support, it's referring that what this x can take. Yeah. So in binomial case, in binomial distribution, the support for x is just all the integer from 0, 1, all the way to n, where n is also defined here. Yeah. So this is the support for x. Yeah. Good question. Yeah. I should have elaborated that a little bit earlier. Yeah. So support is just usually what the value that the random variable x can take. So in our discrete case, or for this particular distribution, it's 0, 1, 2, all the way to n. Let's say n is equal to 10. And then, so essentially you are like tossing a coin for 10 times. And then the support is that you probably will observe 0 heads, or 1 heads, or all the way to 10 heads. So all those values will be considered as supports. So that is the meaning for support. Yeah. Thanks for the question. Yeah. So that's that. And also, so since we just mentioned this in the context of support, in the context of coin tosses, so for the constraint of P, it's just some value that between 0 and 1, because that is the probability that when you're tossing a coin that you lands on a head. Yeah. So this is the support, and this is the constraint for the parameter. And you have two parameters here, n and p here. And also earlier for the exponential distribution, you only have one parameter, which is lambda, and that has to be greater than 0. And that is the constraint for exponential. And this is the constraint for the binomial distribution. Yeah. Okay, then what is the closed form expression for a probability mass function for the binomial distribution? Yeah, I think, yeah, thanks. And yeah, another way that you can think about binomial distribution is that you can consider binomial distribution as like you're doing n times for a Bernoulli distribution. Bernoulli distribution is basically that you're tossing a coin for once. But binomial distribution here, also that we mentioned earlier, is just referring to you tossing a coin for n times. So to think about the binomial distribution, you can think about, for example, first for one tossing a coin for 1 times, you will have the probability of p, and then you also have the probability for landing on head and probability of landing on tail. But because you are doing it n times, and you observe k of them are heads, so you essentially have k times for the probability that landing on head, and then n minus k times for the probability of landing on tails. However, that is only for one particular instance. You can also have like a different instance, like a head, tail, head. That, for example, out of four tosses, this could be one instance. But you can also have the same configuration when you have the head on the 3rd and the 4th instance. So what you need to do here is to consider the permutation. So you have a unchoose k operation here. And this will give you the expression for a binomial distribution. For a Bernoulli distribution, for coin tosses, so you will have x and then 1 minus x. So here the n is essentially 1. So that's for 1 time. But for n times, you need to consider k for k heads, and then n minus k for tail, but you also need to do the permutation, like what we showed earlier. The heads can, even if you have 2 heads out of 4 tosses, they can show up in different location. So you need to have this coefficient here to manage those differences. Yeah. So this is the binomial distribution, and this is the Bernoulli distribution. So that's that. Before we deriving the homogeneous function for a binomial distribution, just from your memory, what is the expected value for a binomial random variable? Sorry, what? Why is that, or any? Yeah. So essentially it's NP, and then it's also intuitive is that, for example, still using a coin tosses example, you toss a coin for 10 times, which is n times. And then, so let's say the coin is a fair coin. So you have a 0.5 probability. So in this case, you out of 10 tosses, you on average, you end up with 5 heads. So that would be your expected value. So n multiplied by p. Yeah. And then what about the variance? Yeah, so here I'm just asking from your memory, and later we will calculate more, let's say, rigorously using moment-generating function to verify these two expressions. So I'm just going to write it down here, and then for us to verify. So what is the variance here for a binomial distribution? So it's n multiplied by p multiplied by 1 minus p. So yeah, so here I'm just going to writing down these two. And now we are going to, again, derive the moment-generating function for binomial distribution. And then taking the derivative, first order derivative, second order derivative, set t to 0. And let's see if we get this and the second moment, and then if we get the variance. So that will be what we're going to do next. So yeah. Is there any question or comments up to this point before we just doing some work? Okay, so now let's derive the moment-generating function for a binomial distribution. And this is for a discrete random variable, so we need to use the summation here. And also, it's all sum over all possible x, which is the support for x. Yeah. And what is the first thing here when you write down the moment-generating function, or in the definition? There's a function called gx. What is gx here? No, I'm referring to the definition of moment-generating function. E raised to the power of tx, right? Yeah. So yeah. So the function gx is e raised to the power of tx, and then multiply by p of x, which is the unchoose. Let me just consolidate the notation. So okay, so since I use x here, then I will use unchoose x. So here it's just referring to n equal to a particular k, like 10 tosses how many, let's say k equal to 5, so that here you put 5 here. But here we're just talking about any general case, so I use unchoose x here, just to consolidate the notation. So px and then 1 minus p, n equal to n minus x. Yeah. So here we just set up the moment-generating function. And next we are just going to evaluate this. Okay, and also here, because we need to evaluate in closed form, so we need to specify x from k, x from 0 to n, which is the support here. Yeah. So we're going to simplify this summation here, and then that expression in the end will be the moment-generating function for binomial distribution. Okay, so let's see. Any thoughts on how we can simplify this? Maybe this is not too straightforward, so maybe let me provide the derivation here. So one thing that we can do here is that we group the terms involving the power of x here. So let's do that, and then unchoose x. You guys know what is unchoose x, right? There's a formula for that, like what are the numbers of yeah, it will give you the number of configuration that give you like the head, tail, that kind of things. Yeah. Okay. And now we're going to group the terms involving a power that involving x. So here we have p multiplied by e raised to the power of t. And then we group these two terms together raised to the power of x. Does that make sense? Because etx also can be considered as e raised to the power of t altogether raised to the power of x. Yeah. So here I'm just grouping the p and the e t, raised to the power of t together, and then they all raised to the power of x. And then you have a 1 minus a p raised to the power of n minus x. Okay. So yeah, here we are going to use another, I'm not sure whether there's a name for that, but maybe let me just write down the equation here. So I think it's called binomial, maybe you can also just look it up and see if there's a name. So okay, maybe let me write down the left-hand side first. So this one, for just to distinguish, here I use k. So k from 0 to n, and then n choose k, and then x raised to the power of k, and then y raised to the power of n minus k. So for this summation here, with this binomial coefficient, this is equal to x plus y raised to the power of n. So this is another result that we're going to use to simplify our expression here. I think maybe this is called binomial. Look it up, the name, please. Yeah, don't take my words for it. Yeah. Okay, but this is the equation that holds. And then we are going to use this expression to simplify that. Okay, so let's see. So what is the x in our case here? So yeah, this x is just the x that only exists in this in this formula. And yeah, so we can consider p multiplied by e raised to the power of t as our x, as this x here, and then this 1 minus p as the y here. And then we also have the power k, the x is the k here, and then n minus x is the n minus k here. Okay, so after we make those changes, let's rewrite our moment-generating function in this expression. So we have our x is p and exponential of t plus y, and y here is a 1 minus p, and then raised to the power of n, and then n again is our n here, so it's that. And this is the moment generating function for a binomial random variables. So yeah, as you can see that it looks different from the moment generating function for an exponential distribution. Yeah. So any question or comments up to this point? Okay, then just to conclude for today's lecture, let's just calculate the e of x by taking the first order derivative with respect to what here? What should we? So I'm asking again. What is the variables that when we work on moment-generating function that we should take in derivative with respect to? T. Yeah. So as you can see, there's only one t here. So yeah. So let me make it. Let also write down the t equal to 0. So there's a prime here referring to the first order derivative. So that's the first step, derivative, and t equal to 0, that's the second step. Okay, so what is the derivative of that? So there's only one t here that in the circle, but we want to take the derivative of that. Well, what is that result? Okay, maybe yeah, because we only have like 7 minutes, so let me provide you the answer. So we're going to apply chain rule again and again because there are the powers, the products, and then also the parentheses. So here we have n that is getting from the power. And then we have the whole expression plus 1 minus a p. And then n minus a 1 here. Okay, now we work on the parenthesis here. Multiply by p. That's the coefficient for the terms that involving t. And then the derivative of e raised to the power of t is the e of t. So that is the first order derivative set t equal to 0. And let's see, we have n and then p e to 0 plus 1 minus a p. And then n minus a 1 p e raised to the power of t, 0. And we have n, and then this is a 1, so p plus 1 minus a p multiplied by p multiplied by 1. So these two cancel out, so you only have n multiplied by p. Okay, so just to going back here, we verify that expectation using moment-generating function, we get n multiplied by p. Okay, let me speed up a little bit for the second moment, because this one is a little bit it takes a little bit longer. So let's see, this is the first order derivative. Now you have t, two terms involving t, and they are in the product, so you need to use the product rule. Okay, so maybe let me just give you the expression. So maybe we can cut in here. Let's see, or maybe cut in. So I'm going to first take the derivative for the part that I underline here, and then multiply by that, and then take the derivative of this multiplied by the whole thing here. That's the product rule. So you will have n multiplied by n minus 1 e raised, let me just finish writing. Minus a p and minus 2, and you have p e t, and then don't forget another copy of et. This is from here. And for the product rule, you need to use a sum, so a plus addition. So you have that multiplied by p e t plus 1 minus p raised to the power of n minus 1. And then derivative of e raised to the power of t is itself. So you have that. So that is the second derivative. Let's just double check. Minus p, that's that, p, that. Yes. Okay. So now we need to evaluate the whole expression at t equal to 0. And let's see. n minus a 1. This is a 1, so this should be 1. Okay, multiplied by p. All both of them are 1. Okay, and then plus n, when you this will reduce to 1, and then n. Am I missing something here? I'm missing a p here. Okay, yeah. Okay, so there's another p here. Okay, coming from here. Yes. When I copy down the part that I underlined here, I'm missing a p here. Okay, so you have a np, and then the rest it just reduced to 1 when you plug in t equals 0, and you have n squared minus n multiplied by p plus np. N squared p minus a np plus np. Somehow I'm missing. I'm missing something. Let me double check. I'm missing another p here. Did someone notice where? I see. When you take the derivative of the chain rule here, so this P is anyway, let me just provide you the answer, and then maybe you can, because I'm a little bit in a hurry, so I'm missing a P, but let me provide you the answer, which is n squared P squared minus a np squared plus np. And this is the second moment. Okay. And then for the variance of x is that n squared p squared minus np squared plus np. And then minus a np squared. So this is the square of the first moment. And then you should have n squared p squared minus a plus np minus a np squared. So these two cancel out. You will have np. So I'm bringing up the np here and then change the order. So this is 1 minus a p from the square here. So np multiplied by 1 minus p. Okay. But double check, there's missing a p here. Yeah, so maybe double check on when you're taking the product rule. Yeah, so yeah, I was a little bit trying to speed up, but I'm missing a p. But the result, this result is correct. Yeah. So yeah, so for this case, binomial distribution, when you use the homogeneous function to calculate that, it looks a little, it might take, it can be a little bit difficult. So you can either use the definition for expectation or using the homogeneous function to calculate the moments, but depends on which one you find it easier. Yeah, that is the bottom line. Okay, yeah. So I will stop the lecture here, and thanks. Yeah, but make sure that there's a typo here, missing a P, I think. Please verify on your own. I will leave it as a homework for you.